never work when they should. So I have to do talk on with shorts, and you will forgive my very bad writings. So let's start with the whole title. That you want to come? Sorry, even the title is something strange, but let's look at this. You see, this is the problem of doing lectures at home without going in presence for 2 years. Properties of PV of a mixing. Well, you can shuffle and many things here, and the meaning is the same in the sense that everything is related to the results, but the order is not what it should. So, so let me start with the question that I was asked from Giovanni Alberti 2 years ago, actually, the last conference before the beginning of the pandemic. So you essentially you consider a transport equation, so the linear transport, and okay, so let's say it's the T rho plus the divergence of V rho equal to 0, and okay, here we are. It's not important. We are not analyzing the properties of the vector field B. So B in our case is 0. We take periodic in time. So, but then we have plus times, and I don't need anything about space. So the torus is enough, and this goes into RD. And since this is not a problem about the regularity of B, I take the B, which is the most suitable for what I want to prove. So in this case, is B is in L. Okay, it's L1t dx, and the divergence of B is equal to 0. So the flow is nearly compressible. Is incompressible. Sorry, and. I don't know if I can write here. Okay. So under this setting is pretty much well known that you have a unique regular Lagrangian flow, which is well, essentially we will see. So there exists a unique flow X T Y with the properties that okay, it solves the ODE. So let's say T. So it's an absolute, so T maps to XTY is an absolutely continuous solution to okay, the X dot T equal to BT X. So there are trajectories of the vector field B, and okay, and here you don't have uniqueness here as a single trajectory. You have uniqueness as a flow whenever you require that the image measure of the back measure is equal to the back measure, so it is incompressible. Okay, so with these two things here, you have a unique flow, and the question that was asked by Giovanni Alberti was what you can say about the mixing property of the flow. So, the mixing property, you can have several definitions of mixings. They are more or less equivalent, but they are not completely equivalent. So the one that I choose here is the one that is more suitable for what I can prove, because it's related to ergodicity. So here the question was, so the question, so now you take the, okay, a priori the question was not about the periodic vector field, but here I take B periodic in time. T of period 1. And then is the problem what if the map Y maps to the flow at time t equal to 1. Y is let's say mixing. And okay, there was just a discussion. So what about mixing here? I say that so the let's say the solution of for every initial data at infinity. So if rho t is unique here in this class, you have uniqueness when the initial data is in an infinity solution. So this is an infinity solution. To the PDE, rho at time equal to 0 is given. Then, so here I said that the rho t quickly converge to, let's say, the average as t goes to infinity. Or essentially here, since doesn't matter t equal to 1 equal mixing means that the image at time equal to 1 when the time equal to 1 when n goes to infinity becomes the average. Okay, so this was the question. So actually the question was how you can identify, is there any nice way to identify that? Because there are already a lot of examples of mixing vector fields. So the problem was well, out of a specific example, can you identify which one are mixing or not? Or can you give some conditions which for which you can say, okay, this is mixing or this is not mixing? And unfortunately, I have this trouble here. Okay, there are other interesting questions here. So for example, now if you touch the class of regularity of the vector field, you may ask how fast you can go to, let's say, if you start with, for example, Lipschitz function, how fast they go to the average, or well, and but here, so since the question was how to identify it, I choose the class that is more suitable for me, which is L1 dvx. And so at the end, what we did is nothing deep, because what we did is that we look at this map T, let's say, equal to the flow at time equal to 1 from the point of view of ergodic theory, and try to adapt what is known for ergodic maps. And so the talk could be finished here. And if I just, well, if you know how to, the tools of ergodic theory, and just try to apply to this setting. So now I'm going to just repeat what is done in that theory and okay, show how you can adapt for this setting here. So that's the thing. Also, I think since it's difficult to follow what is written here, already mix up everything. Probably I need some property, and if maybe I use it, and well, in case I will say, well, otherwise I just forget. You can ask. So the first thing is that the property about the dependence. So the tools in ergodic theory that are the one that I want to use is about you give automorphism of a measure space, and so the maps which perceive measure, and you want to say what is the category, so the category properties, so from the point of view of Baire theorem of these maps. And the result is that essentially, okay, the main tool here is essentially that you can approximate, there is a density property about automorphisms which are periodic. That's the main point. So, so the idea for ergodic theory is that you touch your automorphism a little bit, and then you get a new map which is very close to the original one, but now has the property that you want. And in this case was periodicity. So, okay, I need something related to some property similar to that one when X is not a generic map, but is generated by a flow. because I need to touch the flow in order to get a new map, which is close to my original one, but has the property that I would like to have. So here it comes out the following property, which is, I forget just to cite many people. Okay, all of this theory for BV is done by Luigi Ambrosio, and then another result of Luigi Ambrosio is the regularity dependence. So if you take that under this assumption, so let's say, so here we live in a compact set, we don't need many assumptions that you need to have when you are in some uncompact setting. So here, for example, you need just to have the, let's keep the divergence 0, and you have a family of vector fields with bounded BV norm, uniformly bounded BV norm. And if you maps this to your flow, and so here you take the L1 of Tx norm, and the flow, now you take the correct space here, and you see this is absolutely continuous, so you would like to have the C0 norm on time, and now it's LD, so it is a measure relation in space. So, but since we live in a compact set, we don't, I mean, here the space is L1 of Y, C, T0 of T. And so this map is continuous. Once you know that I keep, I'm inside some, I keep this condition here uniform for the sequence. So, and so this is the first tool that you off-the-shelf tool that you can use, and it replaces the fact that in ergodic theory you are allowed to perturb in L2, so you don't care what if the map comes from some constraint like here, which should be the flow of the vector field. So okay, so let's use immediately this to do something that unfortunately I need. So at least this explanation says why I need BV over there and vector field, no, vector field BV and also mixing. Now, what I do is that I took another tool off the shelf, which is the fact that if you have a function phi, which is defined on some subset of, let's say you have some, okay, some space, let's say, okay, some space, some M, and from A it goes into some another space Y, and okay, so these are metric space, and this is continuous, and M and Y are metric. Then you can extend continuously to a G delta subset containing Y. So there exists U containing A, and this is G delta in M, such that phi is extended and remains continuous. So now if you go back,
goes from A or from M?
phi goes from A. It's defining a subset. And then you can extend uniquely to a G delta set. No, if you require continuity. This is just well, just because the continuity depends on it's open, closed, open sets, then you take the intersection. Okay, so now we apply with this property over here, and so you see that there exists a G delta subset of L1, which contains all the L1t BVX. So corollary, there exists, and then let me call it still set U containing L1tx, G delta set, such that, okay, well, U contains all the BV function. And the property is that is continually extended, and so it's that B maps to, well, phi is continually extended, and here requires that if Bn converges to B in L1, then the flow converges to the flow. So essentially, if you, these are the vector fields for which any regularized approximation converges to a unique flow, which doesn't say that you don't have another flow. Just says that, okay, the good ones are perfectly identified. Okay, and the another important stuff here is that it is a Gδ-set, so I can apply that here. And this was the problem, not because if it is not a Gδ-set, I cannot say.
What's the notion of convergence flow? You fix a label and add convergence, right? That's what the notion of convergence.
Or the convergent flow.
Oh, it's L1t.
It's you take this the integral.
That's what I
Is
mean.
y of the C0 norm.
So the add converge fixed label.
The path, yeah. I mean, okay. The correct, the original one, since it is unbounded, just says that there is a large set where it is converging in C0.
Yeah.
But since here we live in a compact set, you can just replace. Okay, so that's the first of it.
So this U, of course, it's kind of in the closure of the set, right? It's important that it's
contains, clearly, it contains all the good sets where you can prove uniqueness and continuous dependence on the flow.
Yeah.
But it's completely.
It's an abstract category.
It's an abstract set. I don't know. And with that, however, I complete the explanation of the title because the properties. So it ends here. The BV vector fields, they will be mixing, and the properties are the category properties inside this strange set U.
I ask you a provocative question. Are you sure U minus L1t BBX is not empty?
Well, it contains that is.
Yeah, but it could be exactly that. I mean, it could
no.
Itself could be, or is there an easy reason why it's not a G delta?
No, wait a minute. It is a G delta by the.
No, but it could exactly be L1t BBX. I mean, the guy itself.
Well, you have the convolution with the singular kernel.
Ah, okay. So, but it's not a trivial.
It's not a
trivial.
You have the convolution with a singular kernel.
Because somebody else proved that there's something else. Okay. Okay. Good point.
Okay, so so now that's it. And now we start with the ergodic theory. And I'm sorry, because maybe if people know that ergodic theory is really the basic one. Indeed, the literature that I use dates back to the 1940. So, and but I'm sorry. I mean, it's something that is already there, and so first I will invert the reasoning. So why I can use that literature. So now I know that this map is continuous. And then, well, this is a subset of, well, t equal to 1. So let's say that the flows is contained in the set of the automorphism of the torus. Okay, and moreover, I have that this map is continuous. And now I have a category result over there. And since the map is continuous, so you see, then I can just drive back all these results to the set B, no? So a G delta set, the counter image of G delta set is a G delta set. And that's it, that's what I need. So let's say counter image. So that's
pre-image.
The pre-image, yes. Yeah. Okay, I will correct also of G delta sets. Okay, and so now let's look at what people proved in for general automorphism on the torus or general set. So, and now there are the three notions, which is so let's say that the T automorphism is ergodic. If okay, say that A equal to A implies that the measure of A, let me write like this, is or 0, either 0 or 1. And now there was a notion in between. What we would like to have is that T is mixing. And okay, this means that you take T, the iterated of one set, intersection another set, you take the measure of this guy, and this converges to the product of the measures. And finally, there is something in between, which is T is a weakly mixing. And essentially are the Cesaro means of this stuff. They go to 0. So it's a 1 over n. You take the sum n of, well, let's say, En A intersection B minus, okay, is the measure of this guy minus the product squared, and this guy goes to 0. Okay, the squared is because to prove that I mean the density, the use of the Hilbert space is very nice because T automorphism becomes a unitary operator on L2. So that's why the square is nice, but actually it doesn't. You don't care. This is a probability measure, and these things are uniformly bounded because we are in a torus, so you can put whatever. Not the infinity norm, but the rest is okay. And now what do they prove here? The first one is that these two things here are G delta residual, so dense residual sets. And the last one is a first category. So this is the classical theory. I mean, one part of ergodic theory, I mean, concerning the genericity property of this mixing here. So let me. Well, you can find there are very short proof of this thing. So let's see why. I mean, why there is this difference between the mixing and the weakly mixing. So first of all, that these things are G delta sets is you just write which are the family of automorphism which satisfy this property. So for example, for the okay, let's start. I think the ergodic is the easiest one, and the ergodic. So you know that. So you want to prove that, okay, I don't remember which one I wrote first. Okay, now it doesn't come to my mind the condition. I think the condition here is it's 1 over n sum to n of t to the n of a set intersection another set and minus the product of yes, it is 1 the product of the measure. So the difference now is the sum is inside product of the measure, and this thing over here is less than 2 to the minus k. And now you take a base, so ai, aj, ij, and these things is an open set with respect to, well, the topology. And I should discuss also the topology about the T. They use a topology which is called okay, remember the name here. But actually is equivalent in our setting, which is very simplified, is equivalent to the L1 topology.
So that sum is the union, because those are sets. Or am I missing something?
Is the sum of the no, is that the average that yes, this is
okay, that's
sorry, because this is the ergodic theory, not the time averages converge to the space average.
But in there's the square outside and the sum. So
yeah,
you just put okay.
Yeah, that's different because it's like this. Yeah, so and okay, you check, and this is so you have the Birkhoff theorem, which tells you that the space average is equal, for example, to the temporal averages, and this is just the way to use that theorem to rewrite which are the ergodic one. And this is clearly an open set. Now you intersect with respect to ij and k, and that gives you the thing that there exists. So there exists an n, so it's the union, it's open, and then you. And what about the first category? The first category is that you have dense periodic orbit. So the first category, the problem is that you have dense periodic orbit. And clearly, a periodic orbit cannot be mixing. Cannot be mixing. But moreover, if you look at what happened to this sum, you see that they essentially have these bumps no matter what, and even if you touch it a little bit, these bumps they do not go down as they should. This condition. So this is pretty much classical. It's in my note, but now the computer refuses to turn on. So definitely they abandon me.
What does that? Sorry, what does that
sorry, there are automorphisms which are periodic. That's what I wanted to say. Sorry.
So yeah, that's one thing I want to ask. What does periodic mean for?
Means that t to the power n to some capital N is equal to data.
Oh,
So what you're saying is those guys are dense.
Those guys are that. Yes, sorry, not periodic.
And you can't possibly.
This is completely specific.
Automorphism means measure preserving.
Measure preserving. And okay, here is also inverted, just to be having problem. Okay, so that's the stuff, and so now we push everything back through this map, and then we gain immediately the results that for sure they are Gδ-set. So you push back. So we pull back theory. So you get immediately that the T ergodic. So let's say now I have to specify. So I say that the vector field is ergodic when the map is ergodic. So let's say B is ergodic, and for a weakly mixing, RG delta. But I cannot say the density. I mean, can be lost, no? Because it's a subset. I don't know any information about the density coming back. So, and then B mixing is the first category. Well, I have still to verify a little bit. This one, I'm let's see, I have still to verify because I have to prove that the opposite is not is dense. So. Is not true what I wrote down. I mean, I cannot say it can be exactly the image of the flows finish exactly into this first category set, and then it's the full set. So, but later we will see. So let me allow this switching of arguments.
I mean, it's not obvious, but you can prove it.
Yeah, because at the end, I mean, we see that the same as here, the periodic flow whose map is periodic is dense, and that's in fact indeed is the end of the path. So so we have now to work as in this case, so to prove that actually we do something else even better. So we prove now that there exists a dense set of BV mixing vector field, and then we'll fix the problem. So last step. There exists a dense in U set of exponential mixing. Vector fields.
So just from this abstract thing before the last step, the Gδ-set could be empty, right?
Pardon?
This Gδ-set could be empty, right? I mean,
yeah.
So
that's what
this is the last step is actually like.
Actually, there are two and also a dense set of periodic flow, periodic periodic mass. So, and the periodic flows will be used as in the ergodic theory to prove that it's first category. And the exponentially mixing BB vector field is proved to use that they are inside clearly these two sets. And so to say that these sets are G delta dense. and that is the end of it. So, and now,
An exponential will be sharp, right? You can't get double.
yeah, it's sharp, but yeah, the thing is that you see what I mean. At the end, it's elementary. If you know ergodic theory, the fact is that really the fat guy is the witty mixing. And he did, okay, this is my collaboration with my student Martina SISSA, and she came out with an example of a BV vector field, which is weakly mixing, but not strongly mixing. So at the end, this is the natural situation. And okay, before ending, so now the technique is just to prove this two parts here. So before doing that, I want just to say that so the answer to Giovanni Alberto's question is there is a way to check if a vector field is mixing. Well, seems now a little bit strange because I mean, G delta residual set and dense first category set, well, topologically are a nice set, but I mean, as a human, unless you can build the Cantor, the Vitali functions, this start, I mean, it's something that it's difficult to say, no? I mean, it's not that you look to some parameters and then you're sure inside the G delta of the first category. I don't know. To me, these topological things, so that because you can answer the question if you prove, for example, that this set is an open set, then you can expect to have some continuous function, and then you check if this continuous function has some value, and you are fine. Otherwise, here it's complicated. Well, you have a continuous function, you can say the value should be inside some G delta set. You see, I'm eating my tail with this reason. I don't know. This is my feeling. I'm not saying that it's not possible. I'm saying that in this weak setting where you have this genericity property, it seems very difficult for me to give a simple rule to identify mixing vector fields. And another thing that I want to say is that from the point of view of people working in dynamical systems, clearly they have more regularity. And then what happens is exactly what you say. It may happen that this G delta set or this first category set on this subset, which is the maps generated by more regular vector fields, they now become nice open or closed sets. Open set, you want to have open set, not
well, there are these results in very different topology, much stronger topology, that they are wandering. So the results of Schneermann and Derashvili in 2D that you have wandering dynamics. It's exactly.
Yeah. Indeed. The thing is that exactly, indeed. I mean, there are also other results about the genericity of mixing for different classes of
not mixing
or mixing, the Petrosian.
No, that's a different story. These are just saying that the topology in which you measure the G delta or first category matters a whole lot.
Yeah, certainly. And okay, yeah, but this is I mean, this was natural because of this theorem, general theorem. You change it. So let's see now how to do the, and well, you say Schneermann. Indeed, we used some Schneermann tool. That is how to approximate. So now our problem is how to approximate. Give me a vector field. I want to build another one such that the flow as as the property that I want, and so up there. But first of all, the problem is that you need to have a flow which is so simple that you can touch it. Because a priori, I mean, these things, well, you can smooth out, but still remain very complicated. So the idea is taken from Schneermann, which is the following. I take, so there are several results. So the first one is approximate. And now it's, let's say, piecewise affine maps. Flows on dyadic rectangles. Well, dyadic doesn't matter, but you can do that, so why not? Rectangles or parallelepipeds. So let me do in R2, just otherwise I cannot draw it in Focus. Rectangles. So and the idea is really taken directly from a paper of Schmiermann. So essentially, you have this map here, and since I can decide to do the approximation at a small time step, the map is very close to the identity. So it's smooth and very close to the identity. So what I do, I take, for example, my horizontal line here, vertical line here, or my grid, and then I'm looking what happened when you go forward. So this guy over here becomes another curve, well, not level set, but okay, almost level set, and then the inverse of this of the vertical lines becomes this thing here. Just cross. And now what you do? Well,
So your flow is now smooth.
yeah, that you can assume. I need some density property. I'm not
So
genericity. Yes.
Okay.
And now what you do? First, you move along this strip. So, for example, you shift a little bit here in order to make this line vertical. So now what happens is that you have pieces, vertical segments here, and then you do the same in the future. So now you shift vertically here in order to rectify this thing. And when you combine all the stuff, you get something which is essentially, now you have to invert it. So you start with some square, it becomes these green curves, and then they are mapped into the red one. Then you apply the vertical one, the red one, they apply the vertical one, and they become straight. So this is very sloppy way of describing how you combine three flows. So the original one plus some shift to get this map here. If you have more than the dimension is just technical. So, but you see, you can just shift, and the dyadic is because you perturb a little bit the flow in order to have that these lines, they assume value in some dyadic grid. So that's it.
So you told us, okay, so you give me your BB vector field. Okay, so then approximate with which is fine. But then you told me I can assume the map is very close to the identity.
Because once I
Not
do
a time
in a
t.
small time, then I do in the later time, and then I combine the maps.
Okay.
The fine is preserved. Yes.
Okay. It's because you're composing.
Yeah. And so the grid becomes smaller and smaller as the time goes on, because when you combine two, you have to take the intersection, a grid which is finer than both.
Mm-hmm.
And then, but okay, this is not a problem. Just say that there exists some small. So now the next point is, well, this is still fine, but I really would like to have the periodicity. So I want to have the cubes, goes some cubes in a smaller grid goes rigidly to another cube. They just translated to another position. While here, this is affine, no? This is affine. So what you do, well, you just take one of these set here. So I will be imprecise, but let me say that if you choose correctly inside this set, so now you have one set. So let's say you enlarge one of this set and becomes this rectangle, which is mapped to some other strange rectangle. It is affine, and the vertical remain vertical, the horizontal remain horizontal. So now you want to do an operation which, so what you do, you take a smaller grid over here, and essentially you look at, well, you take the grid in order to have that when this rectangle is just rotated. I mean, the boundaries, but not the inside. The inside is, well, it is just you have just to choose the grid which and the eigenvalues of the affine map in order that there is an integer partition of these sets. And okay, believe me, it's just a lot of technique, but you can do that. So, and let me see what happened here. For example, if this is my partition in cubes, I imagine a ratio which is 3:2. This becomes this partition here, this partition here. So it's squeezed and enlarged. And then now the trick is that, well, okay, you can always add the BV vector fields, because if you have discontinuities, you just, it is just in the BV node. That's the advantage with respect to using some other spaces where you cannot do that. I mean, you cannot split along discontinuities the flow. So now what you do here, you turn, and then it happens that it goes back to the original situation. So now when you turn, it becomes, so you rotate inside it. So, sorry, you are rotating the thing inside. So when you rotate, it becomes 2 vertical lines and 1 horizontal line. And then I have to care of the orientation. So here, the orientation, I mean, it's like this, but here, when I rotate, I turn 90 degrees, so I apply another rotation inside each of these smaller cubes. And at the end, if you compose everything together, and there is another observation, is that all these you can do at the same time, because if you see the grid, each grid is not interfering with the other. So I never cross a discontinuity. Inside the grid, my flow remains smooth, so when I add this guy, it's just a deformation of a BV vector. So when I do this composition here, I mean, I start with the beginning, I get that now it maps cube into cube. I mean, the cube is translated rigidly to another cube. And then it means that the map is certainly periodic. But it's not a single cycle, because still I have to touch a little bit. So from now on, I will not go forward. Let me say that once you have that a map maps rigidly, so you have a BV flow which maps, which let's say behave. So you have a small grid, and now you are sure that the cube here goes to another cube in another place and is just translated rigidly. And this happens. So now to end the proof here is that, first of all, if you have a different, well, it is standard. I mean, it's really Ergodic. You just combine the flow, but just, for example, when these two cubes are close, let's suppose that they belong to 2 different flows, 2 different cycles. So you decompose by cycle, and this is another cycle. Well, you just can switch, for example, these 2 when they are close, and now the 2 cycle combines into a longer cycle. So you go around here, and then we go follow the other route. And so I have a single cycle which says that there exists a set which is made by 1 single trajectory, 1 single periodic order. And finally, you have the mixing. The mixing, you take off the shelf any mixer that acts on let's say, on squares. And for example, you decide I will be sloppy again. So let's consider a very easy situation that it's this is mapped into this guy, this is mapped into this guy, it's mapped into this guy. How to make this mixing? Well, essentially, you took the mixer that you like that acts only on these rectangles. And now if you check, so the one that we use is the one of engineer's Latos, because it works in BV, even in more regular spaces. So essentially it has a rotation here. I turn by 90 degrees. And if you check what happened is that, so I exchange and then I turn in these 2 guys, and you combine these things, and then, okay, this is just a problem of Markov chain. I have a Markov chain, which is a periodic orbit, and then I add another matrix which acts on 2, or, well, in our case, we decide to let it act everywhere. And then you check, and the exponents are, there is only 1 exponent with modulus 1. So the rest is the case. Okay, so this is the proof. So let me, I want to say some comment here. So, and the comment is, why do I need to have this Gδ-set, so U, and not to prove directly into the compact set, hence a Gδ-set, which is this space here inside L1. And indeed, we started trying to refine. So the property is all this combination of BV vector fields. What is the BV norm? And the BV norm, well, there are something which is fine. It just increased a little bit of the original BV norm. For example, this perturbation, we didn't do in the paper, but this is a very slight perturbation. You increase the BV norm a little bit. But then the problem is here. Because to map rigidly cubes into cubes, even vector fields which are a small perturbation of the identity will require you to do a large movement of mass. And so if you have something which is a small deformation of this guy, well, you see, I still need to move, in some sense, the mass back. You see what's the problem? And this, indeed, this is of order 1. So at this step, something happened that it is of order 1. The other ones, they can be very small. But something is inside here. Because the rigidity of requiring that the cube is translated into the cube, this is a strong rigidity problem that is not needed for mixing, but is needed for our proof. And so at the end of the thing that you get, if you do this estimate over here, you have that the total variation of your new vector fields is controlled by a constant, the total variation of the initial one. And the constant can be 1 plus epsilon if you're very careful. But then you have a constant 2, which is of the order of the area. And okay, this is the area 1. And that's the why we are not able to stay inside one compact set where you control uniformity's quantity. And so we needed to do this trick, which is very ugly, but okay, we didn't know how to do something better. My student, she's working on another approach that wants to avoid, this construction. So it's more, is not, of course, is not explicit. Because here everything in some sense is explicit. You give me the vector field and I build you the closer one which has the property that you want. And the other is not explicit, will be something implicit and is I don't know yet if it works or not, but she's working. Okay, I think I stop here. Thank you for your attention.
Yeah, so I mean, so why do you, I didn't quite get this. Why do you need to take cubes rigidly onto cubes?
I don't know, again.
Oh, the step where you take cubes rigidly onto cubes?
Yeah.
The bad perturbation. Like, why do you do that? Like, why can't you just conclude some mixing properties directly without that?
Because it is still, well, it is a fun. So I don't know how to touch it. When you compose X, so if Q goes to cube and then you compose X with itself, still cubes goes to cubes. Right. But if you have a rectangle which goes to rectangle, you compose them, then you have a smaller rectangle which are, so you see.
Sure, but like, I mean, they're all matrices, right? These affine transformations, they can be controlled.
But the borders, I mean, this is a rectangle becomes this strange rectangle, and then you apply in a smaller rectangle is affine. Is not is not affine on the same rectangle, the composition.
I see, okay.
You see. And then for rigid instead, it's okay, cubes goes to cube, and then this goes to another.
Okay, but okay, yes, I mean, I'm still, I think you can still do something here, no? Okay,
I could not. I think, yeah, but I suspect so. But then I have this trouble, and the problem is that sometimes you get smashed by the computation, and that is enough. Because they are very complicated. I mean, are not. But it's natural. You believe it. But then to do the computation was not so immediate.
I see. And one more thing I didn't quite catch is, so your result is that it's a dense set in L1 PV, which is ergodic. You can't say that it is like residual or anything in L1 PV.
No, because that's is a first category set.
No, not the mixing, just the ergodic.
The ergodic?
Yeah, just ergodic.
The ergodic, well, the problem is that you have to apply Baire theory. If I understand the question, the problem is, in my opinion, I mean, I had a problem with the Baire theory. So if I use that the fact that the norm increases, so I need to have,
Yeah, okay, yes, yes.
but then this is a first category set. Is the union can't remain a closed set with empty interior, and so I cannot say anything.
Right.
The Gδ-set can be empty.
Sure, okay.
Intersection of it. I mean,
Okay, but yes,
but
but
you
you'd expect that the
you expect, yeah, but
guy to be ergodic or something, right? I mean, yeah.
so the problem is that what you mean by large set, and in first category set, the large set, the category large set is meaningless because you cannot apply that theory. Still, you have the density, yes.
Yeah, but from like you'd expect it, the vector fields which are ergodic will be probably second category, right?
But the problem is that the space is not a space where you can apply that theorem.
Right. Okay, it's fine. Yeah,
That's the problem.
I see.
So the question is meaningless. So the answer is meaningless because it doesn't say anything about the set. It's second category if you cannot apply that theorem.
Okay.
You see, so you can say it's large.
Right.
That theorem is you used to say is large.
Yes.
From the point of view of the bare sigma algebra is large set.
Okay, great. Just
Another question.
Can I ask a small technical question? So here, the operations you're doing, they don't strictly require PV, like this cutting. You might be able to do it with slightly more regular velocity.
Yeah, that's true. Yes. However, we are still in the problem that we have to end up with U, and U, no matter where you start with, you end up with U.
oh,
You start with C infinity, you end up with the same U. So I choose the one that simplifies the thing. I don't need to check any north, just the limit.
Yeah, of course.
So this final problem you mentioned, constant C2, is this related to the rigidity of mappings with which are infinitesimal rotations?
Yeah.
So I guess if you try instead of BB like W1P, P bigger than 1, there would be
And then I have to check if you can do all the operation to arrive at exactly the and divide. I don't know. Yeah, you can. You have other issue for sure. That's for sure.
Isn't the quantitative rigid?
The quantitative, yeah, even more.
There should be a threshold where you lose the property, so because
But this is very difficult, yes. But still, we are
very far from it.
Yeah, because I cannot prove that in this compact set I'm fine. There is a well, that would be very interesting, which is the threshold where you start having nice looking sets.
Probably very hard. Other questions? Nothing in the Zoom. Okay, let's thank Stefano.